Hi everyone, and welcome to this video on the structure module in AlphaFold. I'm Killian Menton, and this video is the 8th and second to last in a series where we are implementing AlphaFold from scratch. The structure module connects the outputs from the Evoformer to actual atom positions, and we already implemented most of what makes it difficult in our last video on geometry. Besides that, there are only two elements that are better explained, and we'll start right off with the first one, invariant point attention. The invariant point attention mechanism directly uses AlphaFold's current hypothesis on the position of the residues to calculate attention weights. A normal attention mechanism looks like this. The network predicts a set of key and query vectors, and they are interpreted as directions. We test how much they align by computing their dot product to calculate the attention scores. In AlphaFold's invariant point attention module, these predicted query and key vectors are instead treated as actual points in three-dimensional space. The query and key vectors of each residue are interpreted as positions relative to the residue's location, and are globalized by applying the transform AlphaFold currently assigned to the residue in this iteration. Now, instead of calculating the alignment of the vectors, AlphaFold calculates their distance to compute the attention weight. Query key pairs that are close to each other get high attention, and pairs that are far from each other get low attention. In addition to using the residue transforms for calculating the attention weights, they are also used to compute the attention values. In invariant point attention, the values for each key are created as three-dimensional points relative to the coordinate frame the key belongs to. The way in which they affect the output for the queries is through calculating the coordinates of the value point in the coordinate system of the query frame. You can imagine that an attention mechanism that assigns attention based on closeness in three-dimensional space can be really helpful for calculating updates to the positions. The query and key positions could be predicted as positions that are highly relevant for the chemical interactions of the individual residues. Standard attention doesn't really have a mechanism to take this into account. The queries and keys are predicted using nothing but the embedding of the residue. However, we probably shouldn't be that hard on regular attention, given that we can see in the attention weights in the Evoformer that the model already assigns attention scores that strongly match closeness in the final predicted structure, as we mentioned several times already. Still, IPA is a clever concept, and it worked arguably well in AlphaFold. So, let's see how the mechanism works in code. The first thing to spot is that the point attention isn't the only contribution to the values and the attention weights. In line 1, we calculate query, key, and value vectors just the way we used to. The local coordinates of the query, key, and value points are predicted in line 2 and 3. In line 4, we compute a bias for the attention weights from the pair representation, similar to how we did it in the Evoformer. And line 5 and 6 compute scaling factors to even out the contribution of the different factors influencing attention: the bias, the normal query key similarity, and the query and key points. Then, in line 7, the attention weights are calculated. The first two terms, dot product similarity and bias, are the same as always. For the third term, the query and key points are promoted to global coordinates by the respective residue transforms. Note that the final residue transforms aren't known at this point, but AlphaFold runs multiple iterations of the structure module, and in each iteration, invariant point attention uses the currently predicted backbone transforms. The distance of the global points is subtracted from the attention weights, scaled by a factor for rating. One part of the weight, gamma, is actually not constant but a learnable factor. After the attention weights are calculated, AlphaFold creates three different attention outputs from the attention weights. The first one is produced by multiplying the attention weights with the pair representation pointwise, then summing the values up along the key dimension. The second is the typical attention output, multiplying the attention weights with the corresponding value vectors, then summing them up. And the third uses three-dimensional points as values. Concretely, the predicted three-dimensional value points are globalized by the transform of the key they are associated with, followed by computing the coordinates of this point with respect to the transform of the query they are calculated for, before summing them up. In the code, the calculation of the coordinates is done by applying the inverse transform of Ti, which can be optimized by moving it outside the summation. All of the different attention outputs are concatenated and fed through a linear layer to get them to the desired output shape. The weighting factors for the different terms are chosen so that all values contribute about equally. Specifically, the three parts, dot product affinity, bias, and point attention, are scaled to have a variance of 1. This scaling assumes that all network outputs are independently Gaussian distributed, which is a common approach when designing layer activations. However, point attention presents a unique challenge, as it's difficult to account for the transforms of the amino acids and quantify their influence on the attention value. To address this complexity, or perhaps to provide the model with more flexibility, AlphaFold introduces a learnable parameter, gamma, to scale the point attention. Gamma is computed as the soft plus, a smooth static function similar to ReLU, of a learned parameter which is initially set to 0. Now that we understood invariant point attention, let's take a look at the structure module. Looking at the code, most of it are just standard linear normalization layers. One thing to note is that the structure module runs 8 times in a row, refining the backbone transforms in each iteration. Each of the iterations uses the same weights, meaning that we don't initialize multiple blocks for this approach. The initial transforms are set to identity rotation and translation 0, meaning all amino acids start at the origin in the first iteration. This is called a black hole initialization in the paper. Each iteration of the structure module consists of the following blocks. First comes the invariant point attention module we just checked out. Then, in line 8, comes a short feed-forward module, the transition. After that, the network computes a transform via the module backbone update and uses it to modify the current transforms by right composition. We discussed in the last video that right composition is generally favorable for updates that cause less strong leverage effects. After the backbone update, the structure module computes the torsion angles using a short feed-forward network with residual connections, the so-called angle ResNet. During inference, it's not really necessary that we compute the angles in every iteration of the structure module, as only the last result is used for the output. The code is structured like this because the loss of the network, which is omitted here, actually uses the predictions of each iteration. It's not only trained to give a good prediction on the last go, but to already give good outputs in every iteration. The prediction of the transforms in each iteration is necessary during inference, both for invariant point attention in the next iteration and because it's iteratively updated. After the structure module ran through, the final predictions of the transforms and torsion angles are used in the method compute all atom coordinates, which we implemented in the last video, to calculate the final atom positions. The feed-forward parts of the structure module are straightforward to implement, and we already covered invariant point attention. What's left is the backbone update. We took a quick look at the code in the last video already. Basically, the network predicts a quaternion and a translation for each residue with a linear layer. The quaternion is normalized to norm 1 and converted to a rotation matrix using the conversion we discussed in the last video. Applying the quaternion to the unit vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1, then stacking those as columns in the matrix. One thing to note here is that the network doesn't predict 4 values, but only 3 for the rotation. The quaternion is constructed by padding with a 1 as the scalar part and then normalizing it. This might be a bit surprising, given that in the last video we stated that for uniform rotation we predict 4 Gaussian values and then scale these to norm 1. The reason AlphaFold doesn't follow this method is due to the iterative nature of the structure module. If we had a single-shot prediction, we would directly want a uniform rotation. However, considering that AlphaFold iteratively updates the prediction in the structure module, it's preferable to have smaller rotations. This is achieved by using a value of 1 for W. By fixing this value, the resulting quaternion is closer to the identity quaternion 1, 0, 0, 0, resulting in a smaller rotation. Note that the direction of the axis of rotation depends only on the vector part of the quaternion, so it's still spherically uniform. With this, we have all the modules that we need for the structure module. It's the last part of AlphaFold, so it's also responsible for gathering all the outputs we need. Concretely, it returns 5 values: the torsion angles, the backbone transforms, the final positions of all heavy atoms, the mask which atoms are actually present in the amino acids, and the pseudo-beta positions. The pseudo-beta positions are used by the recycling embedder for the next iteration of AlphaFold, and they are the positions of the beta C atom except for the amino acid glycine, which lacks a sidechain. For glycine, it's the alpha C atom. One important detail to note is that AlphaFold uses nanometers as the distance unit in the structure module. This is particularly relevant for calculations in the invariant point attention module, and helps ensure that the output has an order of magnitude suitable for neural networks. In the recycling embedder and for the final atom positions, we use angstrom instead, which is larger than nanometers by a factor of 10. To do so, the translation vectors of the transforms need to be scaled by 10. Nothing else needs to change, since the rotations aren't affected by distance. With that, we are done with the structure module. This was a relatively short video because we did most of the hard work in the previous one already. This holds true for the next one as well, where we are putting all the parts together. In the accompanying Jupyter Notebook, you can do the full implementation of the structure module yourself. So, see you in the next video and happy coding!